Now we'll do some problems based on the function. Okay, exercise. Exercise. Let first let f real number to real number be defined by f of x equal x over square root of s square plus 2, so that f is 1 to 1. Find the range of f. Find the range of f. Okay, find the range of f and the suitable inverse and the suitable inverse. Okay, first you want to show that this 1 to 1 mapping, then find the range of f and the suitable inverse. Okay, let x1 comma x2 belong to real numbers. Now you take f of x1 equal f of x2. Okay, f of x1 equal f of x2. F of x1 equal f of x2 means x1 over square root of x1 square plus 2 equal s2 over square root of s2 square plus 2. So implies x1 squared s2 squared plus 2 s2 squared s1 squared plus 2. Now you simplify this one, you get s1 squared minus s2 squared equal 0. This one implies s1 plus x2 x1 minus x2 equals 0. From this both you get okay, from this both you get x1 equal x2 or x1 equal x2 or s1 plus s2 equals 0. It is not true because x1 s2 are same sign, positive, right? s1 s2 belong real numbers. For this case we can't get 0 values here. Suppose x1 is positive, s2 also positive. Therefore only possible, it's not possible, therefore only possible x1 equal x2. S1 S2 are positives, right? S1 S2 are positive, then how can you get 0 values? Suppose x1 positive, then S2 minus means they are not equal. That is not the case. Suppose S2 minus, S1 minus, S2 also minus, then how can you get the positive? Therefore, it is not a possible case. Okay, therefore only possible is not true because S1 S2 S1 S2 are same sign. S1 S2 are same sign. S1 S2 are same sign. Okay, therefore S1 equal x2. S1 equal S2 means f is 1 to 1. Now you want to prove that for a 1 to condition, not onto range, no? Okay, let's find the range. Let y belong to real number. You have y equal f of x. F of x equal x over square root of s squared plus 2. Then from this one you can multiply here y squared s squared plus 2 equal s squared. This one implies, okay, 2y squared equal s squared into 1 minus y squared. This one implies x equal square root of root 2 y over square root of 1 minus y squared. Here negative sign is rejected because f of x equal y have the same sign. No? X and f of x equal y have same sign. Then how is it possible for? Suppose here y belong real number means x also, suppose here y positive, they have x also positive. Y is negative, then x also negative. Because y is in terms here, it is suppose it is negative, this one negative. Suppose this one positive, this one positive. Negative sign. Rejected. Because s 2y squared, x squared equal 2y squared over 1 minus y squared. Then take the square root of x equal plus or minus root 2y 1 minus y squared. Okay. Be here rejected minus term. Suppose x equal minus y, it is not possible. Okay. In both places are both sign. Here plus sign means here also plus sign. Here minus sign means here also minus sign. Okay, the sign negative sign is rejected because x and y have same sign. Okay, because suppose you have put here plus sign, it is obviously plus sign. Suppose you put here plus sign, here also you want to get plus sign. Okay, right. Now you found the x values. The question, you want to find the, obviously this y squared. What about the y squared? For any values of x belong real number, what about the y squared value? What about the y squared value? Okay. What about the y squared value? Since x belong to real number, okay. Obviously, this y squared less than 1, no? Y squared less than 1 means minus 1. I take the y between minus 1 plus 1. Because suppose y squared less than 1 only, this is real roots, or complex roots. Therefore, a real number or a function real number to real number. Therefore, you want to get here real number. Therefore, y squared should be less than 1. Therefore, your range of y is minus 1 to plus 1. Okay. Now, therefore, it is y is your range, no? The range of f, what is the range? Minus 1 plus 1. Okay, minus 1 plus 1 your range of the function. Then you can find the inverse, and so if it's a function from real number to what is the range? Minus 1 plus 1, right? Is 1 to 1 and onto function. We already proved 1 to 1 and onto function. Okay. Therefore, 1 to 1 onto function means, therefore, f is invertible. F is invertible means f inverse exists. Now you can find the f inverse. Now your f inverse mapping from here to here. Minus 1, 1 to real number. What is a mapping? F inverse of x. You know, f inverse of x means, f inverse of y means what is thing? F inverse of y means root 2y over this one. Root 2y over square root of 1 minus y square. It is f inverse y. It is your x, no? It is your x. f inverse y, because f is only means f of x equal to y. Therefore, x equal f inverse y. F inverse y equal to this one equal to x. Okay, it is your inverse mapping. Now you can replace. Now replace y by x. You can replace y by x, then you get the inverse mapping f inverse x root 2x over square root of 1 minus s square. It is your inverse mapping. Root 2x over square root of 1 minus s square. Okay. Now another question. Now we will do this problems. Okay. Now another exercise. F is a function from to integer number to natural number defined by f of x 2 modulus of x. If x less than 0, 2x plus 1. If s greater than 0, greater than equal 0, first you want to find the inverse of f and the values of inverse. For first, suppose this mapping have inverse mapping means first you want to show that f is biexcel. Okay, then f is biexcel means f is invertible, therefore f inverse x is. Okay, first you want to show that it is a biexcel function, right? Because so that for this question, so that f has an inverse, all right. Therefore, you want to find the inverse. Find f inverse okay. Now first you take f of x1 equal f of x2 for a case 1 for this part, right? Case 1 means suppose both are negative, that means s1 less than 0 and s2 less than 0. Suppose s1 less than 0, s2 less than 0 means you take f of x1 equal f of x2. F of x1 means 2 times modulus of x1, 2 times modulus of x2. Here x1 s2 are less than 0, no? Then modulus value minus 2 x1 minus 2 x2. Then you can cancel the minus term, then you get x1 equal x2. S1 equal s2 means, right, s1 equal x2. Next case, right, there are 4 cases there. Suppose now we take s1 less than 0, s2 greater than 0. What happened? For a case 2, suppose s1 less than 0, okay, and s2 greater than equal 0. For this case, you take f of x1 equal f of x2. F of x1, s1 less than 0, no, we have a 2 modulus of x. But here s greater than equal 0 means 2 x2 plus 1. But here its modulus value minus because it's s1 less than 0, minus 2 x1, 2 x2 plus 1. This one implies 2 times x1 plus x2 equal minus 1. This one implies x1 plus x2 equal minus half, which is not possible. Why? Which is not possible because, right? Because here x1, x2 belong to integer numbers. Therefore, how we get this fraction number again? Addition fraction number. Therefore, second case 2 cannot arise. Okay. Therefore, second case not possible. Right? Suppose s1 less than 0, s2 greater than equal to 0, not possible. Case 3, s1 greater than 0, s2 less than 0. Okay. For a case 3, s1 greater than equal to 0 and s2 less than 0. For this one, you take f of x1 equal f of x2. F of x1 equal f of x2. Here, x1 equal greater than equal to 0 means second case. 2x1 plus 1. s2 less than 0 means you take 2 modulus of x, here, x2 less than 0, then you get 2x1 plus 1 minus 2x2. Now, 2 times x1 plus x2 equal minus 1. So, implies x1 plus h2 equal minus half. It is not possible because it is not possible again because here your x1 comma x2 belong to integer number. Or you add 2 integer numbers, you can get another integer number, right? You can't get the fraction number here. That is not possible. Now case 4 based on the s1 less than s1 greater than equal to 0 and s2 also greater than equal to 0. For this case, we take f of x1 equal f of x2, f of x1 equal to 2x1 plus 1, 2x2 plus 1. From this one implies x1 equal to s2. Therefore, for first case and last case only it is possible. That means both are same sign. First s1 less than 0, s2 less than 0. First case. Last case s1 less greater than equal to 0, s2 also greater than equal to 0. Then the two case only is mapping. It is one to condition satisfying. Therefore, for the all cases you can tell, right? Therefore, f is 1 to 1. Okay, f is 1 to 1. F is 1 to 1 for a suppose s1 s2 are same sign. That means f1 s2 are s2 are greater than equal to 0. F is 1 2. For this case 1 2, this case 1 2. Therefore, altogether this mapping is of 1 to mapping. Sorry, this case 1 to 1, this case 1 to 1. Therefore, altogether this f of x is a 1 to 1 mapping. For one value you take here one values, here one values. That was not possible to here. Therefore, that is not a 1 to 1. Here, this case 2 and case 3 not possible. Okay, case 1, case 2 only possible. Now you want to show that if it's a 1 to function, right? Okay. Now we shall show that if it's 1 to. Now we shall show that if it's 1 to function. Now we shall show that f is 1 to. Here let your y belong to the natural number. There are two cases. Case 1, suppose y is even number, then you can write let y equal to 2k for some k belong to natural number. For some k belong to natural number. For some k belong to natural number. For some k belong to integer number, sorry. Integer number. Okay. Therefore, this minus k also belongs to integer number, no? Minus k also belongs to integer number. Therefore, obviously minus k less than 0, right? Such that, therefore, what is the f of minus k? F of minus k equal to 2 modulus of minus k. Obviously, this modulus is plus k. Therefore, 2k. But what is 2k? 2k is your y. Therefore, y is onto mapping, right? That is for this case. That means here f of, right, f of right, minus k, no, minus k equal to minus y by 2. Yeah, minus y by 2 case. Minus y by 2 means, okay, minus y by 2. To put k as minus k as minus y by 2 equal to y, right? Right. Yeah, but it's onto function, right? You have the function, right? F integer number to natural number, okay? Integer number, natural number. Now we take the y values here, okay? Y. You can find the values here. You find here minus k. Therefore, f of minus k equal to y. It is shown to condition. Okay. Case 2. Y is odd number. Then you take the idea y equal to 2m plus 1. Here m belongs to natural number. For some, here m greater than equal to 0 and m belong to integer number. Here k less than 0, minus k less than 0 only first case possible. Here greater than equal to 0 for second case, right? What is the f of m? M belong to integer number, right? M belong to integer number. What is the f of m? F of m equal 2 times, right? 2 times here m is positive, okay? M is positive. Then you can use f of m is equal to f of m means from the formula 2m plus 1 means 2m plus 1 equal y, right? That is, that you want to find the f inverse. Therefore, f inverse, sorry, you want to find this f of, okay, f of, what is the m? M means y minus y by 2. Is it okay? This value is equal to, right? This value is equal to, here, y minus 1 by 2 equal m, no? Here, y minus 1 by 2 equal m. Y minus 1 by 2, okay, right? 2 times y minus 1 by 2 plus 1. What is the value you get? Y. Therefore, f of y minus 1 by 2 equal to y. For this case also, mapping is, hence, f is on true. Because this condition also satisfying for f is f is odd number case. It is f is even number case. Oh, sorry, y is even number case. Y is odd number case. This one satisfying. Y is even number case. This one satisfying. Therefore, function f is onto function, right? Already proof f is 1 to 1. Here onto function. Therefore, f is by xn. Okay. Suppose f is by xn, right? F is by xn. Therefore, f inverse exceeds. F inverse exceeds. They asked to find the values of, like, f inverse exceeds, okay. They asked to find the values of, which values? F inverse of 5806. Okay. Since you know that 5806 is even, no? Even number. 5806 is even number, no? Therefore, which case is possible? F inverse, you know, right? You know, this part you want to find it, okay? This part you want to find it. This one even, now you put here, in this question, here, even case you put here, f of y is this value, f of minus 5806 by 2 equal your y. Therefore, this one f of minus 2903 is your y. Therefore, minus 2903 your f inverse y. Y means this is your y value. That means f inverse 5806 equal minus 2903. Right? 2903 minus 2903. Is it okay? It is your y values. Y is even. Obviously, 5806 even number, no? Then use this first condition. Then it's onto mapping. Then you can take the inverse f inverse y equal to y minus f inverse y equal to minus y by 2. Okay. Next question. Next question. You want to find the composition function for 3, exercise number 3. You want to find the composition function. Here your function is this one, 0,32 real number defined by f of x 1 plus x 3 minus x 0 less than equal x less than equal to 2 less than equal x less than equal 3. You want to find f composition f composition f. Okay, you want to find the f composition f. Case 1, for this case. Case 1, basically 0 less than equal is less than equal to. Right? Then suppose you add here 1 less than equal x plus 1 less than equal 3. It is your f of x. 1 less than equal to f of x less than equal 3. Therefore, the range of the f of x is 1 to 3. Therefore, we can separate this interval in other cases. For this small I case, right, the interval f of x up to 2 equal to. Another case, sub cases, another case 2 less than f of x greater than equal 3. Right? For a case 1, there are sub cases there. This case. For this case, we want to check first. Now, for this case 1, you consider this case, this case. Okay, this case 1 less than equal f of x less than equal 2. That is 1 less than equal x plus 1 less than equal 2. Then 0 less than equal x less than equal 1. For 0 less than equal x less than equal 1, this case, right, your f composition f of x, you want to find it. Okay, f composition f of x, it is f of x. F of x becomes x plus 1. Okay, x plus 1. Now again, f of x plus 1 means what do you put? X plus 1 plus 1. Therefore, x plus 1 plus 1, x plus 2. Therefore, x plus 2. Sorry, 1 plus x. Just 1 plus x. Okay, 1 plus x. 1 plus x means then again 1 plus x. Therefore, 2 plus x. Okay, 2 plus x. Okay, 2 plus x for this thing. Now, for the small case 2, right? For a first case 2, right? Case 2, we put small small number here. Now your case is, right, case 2 means this case 2 less than f of x less than equal 3. 2 less than f of x less than equal 3, right? Here 2 less than x plus 1 or 1 plus x less than equal 3, then you get minus 1 2, sorry, 1 less than x less than equal 2. For this case, your conversion f of x, what's the value? Here, first 0 to 1, right? 0 to 1, 1 less than x less than 2. For this case, your values f of x. F of 1 plus x, no? F of 1 less than 2 here, very important things there. 1 to 2. 1 to 2, what is the function value? 2 to 3, that values. X is 1 to 2. But here, your f of x means, right? F of x means, right? F of x means, f of x, take the value 3 minus x when 2 less than x less than equal 3, no? Okay, no? This case, your f of x values, which values? 3 minus x. Therefore, f of 3 minus x. F of 3 minus x means 3. Is it okay? F of 3 minus x means 3. F of 3 minus x means, sorry. X, take the value 1 less than equal 2. Okay. For this part, 0 to 1. Here your range is 1 to 2 means f of x take the value x plus 1. But for a 2 to 3, your f of x take the value 3 minus f of x. But your f of x, right? Your f of x means here x plus 1. Therefore 2 minus 1 plus x. Therefore you get 1 minus x, no? Is it okay? Sorry, here 3. 3. Therefore, 2 minus x, okay. 2 minus x, right? For that case. For in this case, for your values of this f of x, f combination fx. Okay, right. This case, your x value range of 1 less than equal x less than 2 equal to. Okay. Now, for this case, for 2 to 3. Now 2 to 3 case should be case some cases of is 2 to 3 x 2 to 3. Now you want to find the f of x range 3 minus x, no? 3 minus x. You can minus 2 greater than minus 6 greater than equal minus 3. Minus 3 plus 3 minus x plus 3 less than minus 2 plus 3. You can have 0 less than equal 3 minus x less than 1. Right? 3 minus x is your f of x. F of x less than 1. 0 less than equal f of x less than 1. Yes. Now you want to find the f composition f of x. F of x 0. Or this value here. 1 plus f of x for this f of range. Now, okay, 1 plus f of x, okay. Now, 1 plus, what is the f of x for this x range? It is f of x function. F of x function range is one. Why use here 3 minus f of x? Because here you want x, f of x function. F of x function range 2 to 3. F of x function 2 to 3 means your function becomes like this. You put x here f of x, here also f of x, 3 minus f of x, right? Like that here, f into f of x. F of x is a function, right? The range of f of x is 0 to 1. Therefore, first case, arise the first case. S is f of x. First case. Therefore, 1 plus f of x. Now, you consider x value. X value 2 to 3. X value 2 to 3 means this case. 3 minus x. Right? 3 minus x. Therefore, 4 minus x. Therefore, your f composition f function, there are 3 functions there. First 2 plus x function. This interval 0 less than equal less than 1. 2 minus x, another function. 1 less than x less than equal to another function 4 minus x, right? 2 less than x greater than equal to 2. Sorry, greater than equal to, so less than equal to 3. Okay, these are the ranges of this function f composition f. Okay. Next question. Next question. Next question. f is one of the function. Let f is one of the function, real number to 5 comma infinity, and g is another function, that one also 5 comma infinity to real number defined by f of x equal to 2 power 3x plus 5 and g of x equal 1 by 3 log x minus 5, so that f and g are inverse of each other. So that f and g are inverse of each other. Let you want to show that, suppose f is the inverse of g and g, or otherwise g is the inverse of f. Therefore, this f composition g is identity and g composition f also identity. You want to show that f composition g is identity and g composition f also identity for this question. Okay. Now let x belong to real number. You consider this mapping g composition f of x. G composition f of x means g of f of x. G of f of x means f of x is one, 2 power 3x plus 5. Right? We have some theorems like the function. Suppose it is the inverse of that one. Therefore, you get for composition is identity mapping. We check 1 by 3 log base 2. Okay, base 2 log 2. What is the value? X is 1, 2 power 3x plus 5 minus 5. Then you can take inside 1 by 3 into 3x time log 2. Base 2 is 1, therefore 3 you can cancel, you get x. X means identity, no? That is g composition f equal I real of x, again x. Here x means I real of x. Now let x belong to 5 comma infinity. F composition e of x. F of e of x. F of g of x, this value 1 by 3 log 2 x minus 5. 1 by 3 log 2 x minus 5. 2 times 3, 1 by 3 log 2 x minus 5. Okay, plus 5. This 3 cancel. Log 2 times, okay, 2 times log 2 x minus 5 plus 5. Suppose e power log ln x minus 5 means x minus 5. Like that, 2 power log 2 x minus 5 means this value is x minus 5 plus 5. 5 cancel, you get x. Here also, therefore, f composition is I real. I 5 comma infinity. Okay, for these cases we get the identity mapping. Okay, therefore we can therefore this enough to show that f and g are inverse of each other, right? Suppose f is the inverse of g or g is inverse of f. Okay, the way enough to show that which is f and g are inverse of each other, right? Now another exercise. 13. Exercise 5. If a to a be a real value function, define on a set A of real number such that f inverse x equal to 1 over f of x. And also you want to show that suppose a 0 not equal to a, therefore f of to the power 4 equal ia. Identity mapping. Okay. For this question, let f a to a be a real value function. Defined on a subset A of real number such that you have f inverse of x equal 1 over f of x for all x belong to real. So that for one condition, so that 0 not equal to a and f to the power 4 equal I a. F to the power 4 equal ia. Okay. Okay. Now let x belong to a. We take one of the element x belong to a. We saw that we will show that we shall show that x not equal to 0. We shall show that you have, since you have f inverse of x equal 1 over f of x for all x belong to a. Therefore, this one exit, right? Such that this one exit means definitely this f of x not non-zero, no? It's not defined. Therefore, f of x non-zero for all x belong to a. Okay. As f is your function a to a, here if each of f of x belong to a for all a to a, no, a belongs, sorry, for all x belong to a, for all x belong to a. So far, suppose you have another, sorry, this value x dash equal f of x. Okay, x dash equal f of x. This one belong to a. Suppose this one belong to a means this f of x for any values of x non-zero, no. Therefore, this f of x dash also non-zero. Because for any values of x is non-zero, right? For any values of x is non-zero, right? For x or x dash, for any values of x non-zero. Now you shall show that is x equal to 0. X equal to 0, then you want to show that x equal to 0. X means I of A of X, identity mapping. I of A means you can write F inverse composition F of X. This one you can write F inverse of F of X. Okay. F inverse of F of X means 1 over F of X. Okay, this one 1 over F squared of X. Obviously this one non-zero because otherwise not defined. Therefore X non-zero. Therefore X non-zero. X is one of the element of A, right? X is non-zero. You know, if of X non-zero, okay, but now you want to prove that X also non-zero because X belong to A. For A, you want to show that A non-zero. A non-zero means, right? A non-zero means for any values of X, right, belong to A, that one non-zero. Here, X is non-zero. Therefore, X non-zero. Now, we have from this part, we can go to that from that part, S equal 1 over F squared of X, right? Therefore, your F squared of X equal 1 over X. For all X belong to A, X belong to A, and also X belong to A and X not equal to 0. Now, okay. Now, we take this one, F power 4 power X. F squared into F squared of X, okay? This one, F squared of 1 over X. So again 1 over X. It is your X. It is your I of A. Okay, I of A of X. For any values of X, therefore F power 4 equal I of A. Therefore F power 4 equal I of A. Okay, F power 4 equal I of A. Now, next question. The composition function 1 to 1 means suppose if and g are two function, if and g are 1 to 1 and if and g are 1 to 1, therefore f composition g also 1 to 1, but converse need not be a true. Okay, like that, if and g are 2 onto function, is f composition g also onto function, but converse need not be a true. And two exercise we do next, right? We'll do next. Exercise 6. So that there are two parts. So that the composition of the composition of 1 to 1 function. Okay, composition of 1 to 1 function injective function. 1 to 1 function or injective function uh, is 1 to 1. But converse is not true. But converse is not true. Not true. Therefore, you want to give the counter example. B part, so that, right? B part, so that the composition of two onto function is onto, so that the composition of two onto function is onto, but converse is not true. But converse is not true. Okay, let's you take f be the function for a part, f be a function a to b, and g be a function b to c be one-to-one function. Then you can prove g composition f a to b, no? A to b is a function from a to c, a to c. So now you want to show that g composition f is one-to-one. To show that g composition f is one-to-one, because f is one-to-one, e is one-to-one. Let to take element two element, g composition f of a1 equal g composition f of a2. Suppose g composition f of a1 equal g of f of a1, g of f of a2. Suppose g of f of a1, g is on to one-to-one, therefore f of a1 equal f of a2, but f also one-to-one, therefore a1 equal a2. Therefore g composition f is one-to-one. Okay, g composition f is one-to-one. Now now the converse part is not true, therefore you want to give the counter example for this part. Okay, this part, let you take the set a as one of the set 1 2 3, b another set 0 1 2 3, c another set 2 3 4. Okay, 2 3 4. Okay, now f of a equal to a minus 1, f of a equal to a minus 1, your now your f is a function from a to b and g is a function from b to c. Now your f of a becomes a minus 1, right? E of c, e of e b c function is defined by like this. Here g of 0 equal 2, g of 1 equal 3, and g of 3 equal 4. And g of 3 equal 4. What is the g composition f of 1? Here we take e is a function here. What else? E2, E3, 4, and G4 also, E2 also 4, E2 also 4, E3 also 4. Therefore, suppose here both are equal, but 2 not equal to 3, therefore obviously E is not 1 to 1. What about decomposition f of 1? Decomposition f of 1 means E of f of 1. F of 1 means you put here A as a 1, 1 minus 1, 0. Therefore, E of 0. E of 0 equal to 2. Right? E of 0 equal to 2. Decomposition f of 2. Right? Decomposition f of 2. Here E of, right? E of f of 2. F of 2 means 2 minus 1, 1. Therefore, g of 1. G of 1 means 3. Therefore, similarly, g combination f of 3 equal g of f of 3. G of f of 3 means 3 minus 1 means 2. Therefore, g2. G2 equal to 4. Right? Now, g of combustion f, you can take only 3, no? To 3. There's no 4. Okay. Okay. For these cases, you can take here. Suppose you take here not equal. Suppose you want to show that this one-to-one mapping. There are two ways to one-to-one. There are two ways there to show one-to-one mapping. Right? There are two ways there to show one-to-one mapping. It is another way. Suppose here this elements not equal. No. Suppose here 1 not equal to 3. Sorry, 1 not equal to 2. Therefore, you want to show that f combustion g. No. So g combustion f. This one was not equal. G combustion f of 1 not equal g combustion f of 2. No, because g combustion f of 1 value is 2. G combustion f of g combustion f of 2 value is equal to 3. 2 not equal to 3. Okay, 2 not equal to 3. Therefore, from this condition, this one satisfying. Therefore, this one also 1 to 1. Okay. Therefore, G combustion F is 1 to 1, but G is not 1 to 1. Okay. G is not 1 to 1, but G combustion F is 1 to 1. Okay. Right. Next part, you want to show that the combustion of two onto function is onto, but converse need not be a true. Converse part. Okay, let for B part. Okay, for a B part, let f is a function a to b, and e is another function b to c, b onto function. Then E composition f is a function from A to C, from A to C. We want to show that E combustion f is onto. To show that E combustion f is onto. Let you take one of the element. Here E combustion f is A to C, no? A to C. Therefore, C belong to C. Since E is onto, B to C is onto. Okay, there exists B belong to B such that E of B is C. Again, F also A to B, no? F is onto, right? F is onto, so there exists A belong to A such that F of A you put that name B. Okay, F of A equal B. Second one, for all, for all B belong to B, there exists A belong to A such that F of A equal B. First condition. Second condition, from using both condition, you take this function E of f of A. E of f of A means B, no? Therefore, E of B equal to C, right? E of B equal to C means E combustion f of A equal C. That means A belong to A, and there for all A C belong to C. There is A belong to A. This E combustion A equal C. Therefore, E combustion F is onto mapping. Converse need not be true, and converse need not be true. Therefore, we want to give the counter exam. So take let A be this set 1, 2, 3, B be another set A, B, C, D, and C be another set X, Y, Z. Let your function A to B and G another function B to C. Here they define G composition f of 1, they put X. They define G composition f of 2 is Y. This G composition f of 3 equals Z. Therefore, here it's 1, 2, 3 and C X, Y, Z. Therefore, it's onto mapping. No, obviously this G composition f is onto mapping. It's okay. But f of 1a, f of 2c, f of 3d, f of 1, f of 1a, f of 2c, f of 3d. Therefore, these remain. There's one of the element. There's no assign. There's no pre-match to b. Therefore, it's not onto. That f is not onto. Okay, f is not onto. There's no pre-match part. Okay. Okay. It's the count example for that part. Okay. Exercise. Prove the following. The following. First one, if a to b is a biaxial, if f is a function a to b is biaxial, then your f inverse b to a is unique. Second part, if a to b is biaxial, then F inverse B to A, this one also biaxial. For first part, suppose A to B is biaxial, then F inverse is unique. The inverse mapping is unique. Okay. Let F A to B is biaxial. Then you can find two inverse of this F. If G B to A and H another B to A, B2 to inverse of F, 2 inverse of F. Now let B belong to B, right? They are like this biaxial function of F, B belong to B. Okay, let B belong to B. They are like this. You can take A1 belong to A such that G of like G of B equal to A1. Just that is condition. G of B equal to A1. Okay. Then F is a biaxial function. F is a biaxial function. Therefore, F of A1 belong to A1. No? Therefore, F of A1 equal to this B. Okay. Similarly, for all B belong to B, they are like this A2 belong to A such that another function H, no? H of B equal A2, but here F is 1, 2, therefore F of this A2 equal another value, F of A2 equal to B. Because F is biaxial, no? Therefore, F of A1, suppose F of this both are equal, no? Suppose F is 1 to 1 means F of B equal to B, therefore F of A1 equal to F of A2 means A1 equal to A2. Right? This means for this one, F of A1 equal F of A2. So if it's 1 to 1, therefore A1 equal A2. Right? A1 equal A2 means that A1 equal A2 means G of B equal H of B for any values of B belong to B. G of B equal H belong to B for any values of B belong to B. Therefore, these two functions are equal. Therefore, that inverse function is unique one. Okay. Therefore, inverse function is unique one. Therefore, F inverse is unique. Therefore, F inverse is unique. Therefore, F inverse is unique. Now, second part. Let, for the second part, let F A to B is a biaxial. From the previous part, we already proved F inverse B to A is unique function. F inverse B to A is unique function. First, you want to show that for this part, F is F inverse is 1 to 1 and on. To prove that F inverse is 1 to 1, first case. To prove that F inverse is 1 to 1. Let you take B1 not equal to B2, right? here b1 comma b2 belong to b. Therefore, you want to show that f of b1 not equal to f of b2. Okay. Let f inverse b1, f inverse b1 equal a1, and f inverse b2 some a2 for all a1 a2 belong to a. From this one you can write f of a1 equal b1 and f of a2 equal b2. But b1 not equal to b2, therefore b1 not equal to b2, therefore a1 not equal to, right, b1 not equal to b2, therefore f of a1 not equal to f of a2. Here f is a1 comma a2 belong to a, right, a1 comma a2 belong to a, therefore f is 1 to 1 and 1 to, right, f is 1 to 1 and 1 to, right, f is 1 to 1 and 1 to, suppose you take f of a1 not equal to f of a2 means a1 also not equal to a2 because f is 1 to 1, right, f is 1 to 1, a1 not equal to a2 means f inverse b1 not equal to f inverse b2, f inverse b1 not equal to f inverse b2 means f inverse is 1 to 1, f inverse is 1 to 1, f inverse a is 1 to 1. Okay. Now f inverse is 1 to, right, because you want to show that bijection now, therefore now remaining you want to show that f inverse is 1 to. Okay. To prove that f inverse is 1 to, okay, second part, to prove that f inverse is 1 to prove that f inverse is 1 to, let a belong to a, this b belong to b such that, right, such that f of a equal to b, so implies a equal to f inverse b. You want to show that f inverse b is f inverse here, f inverse is bijection, but f is bijection, no, from the f is bijection. Okay. Okay, that is for all A belong to A, direct is B belong to B, such that F inverse B equal A. Right? F inverse B equal A means F inverse is 1. F inverse is 1 to, therefore, all if of F inverse is 1 to 1. Now we prove F inverse is 1 to, therefore, F inverse is bijective. Okay, F inverse is bijective. From this F is 1 to know, then you can write this part. F is 1 to, right? From that one you can write this part. Okay. Now this exercise, I think 10 to F of x equal x plus 1, x minus 1, x not equal to 1. There are two parts they asked, so that A part is for conversion mapping of x again x. Again B part 5 conversion map of x again f of x. These two parts we want to prove. Okay. Let you want to prove these two parts. Let your f of x equal x plus 1 over x minus 1, x not equal to 1. Now, right now, f composition f of x, what is the value? F of x. F times f of x becomes x plus 1, x minus 1. Therefore, f of x plus 1, x minus 1 becomes x plus 1, x minus 1 plus 1, x plus 1, x minus 1 minus 1. Now, you simplify this one, get x plus 1 plus x minus 1, x plus 1 minus x plus 1. Then minus 1 minus 1 cancel, x cancel. Therefore, 2x over 2 becomes x. 2x over 2 becomes x. Okay, 2x over 2 becomes x. A part. Now your B part. You take first. Now you have. Okay. Okay. Sorry. This 2 conversion function. Okay. Now we move to the 3 conversion function. Right. What happened? This. Not a B part. F composition, f of x. This one f composition, f of x. But you already proved this f composition f of x already proved is f composition f of x. F into f composition f of x already proved x is f of x. Now up to 4. 1, 2, 3, 4. This one f of up to 3 f of x. Right? This one f composition f of x. But f composition f of x means x. Now B part. Here 5 to 4 there. Now move to 5. 1, 2, 3, 4, 5. F of x. Up to 4 your values. Right? Up to 4 your values. For this part your values f of x. F of x means x plus 1 over x minus 1, x not equal to 1. Okay, right. Okay, okay.